The second learning sequence in block number 2 will be about hypothesis testing, one of the probably most used but also most difficult for understanding, especially for beginners. Very often hypothesis testing is not used correctly, or the results of the hypothesis testing are not correctly interpreted, and therefore it raises a lot of confusion and even long scientific discussion. So let's consider hypothesis testing. Let's learn hypothesis testing very slowly with a lot of examples to avoid any confusion, to make sure that you understand this well. Let's start with something that we already know, partially at least. It's a hypothesis testing about average of population based on the average of sample, which we know already is that we are going to use t-distribution for that. So let's talk about one sample t-test. You remember what we also discussed in the previous learning sequence. We have a population with some parameters which usually we don't know, and then we have a sample which statistics we always can compute because we can just measure the sample characteristics and compute different statistics, for example, average, standard deviation, and so on and so forth. In the previous learning sequence, we learned how to estimate parameters of your population based on the sample statistics using confidence interval. In this learning sequence, we will do a slightly different thing. We will learn how to assess if your sample came from population with given parameters. So we have an assumption, we have some expectations about parameters of population. For example, in this particular case, you can see I expect that average sugar content in all apples of the population is not below 10. So it's 10 grams per 100 gram of apple mass or larger. So it means that I expect that apples are sweet in this population. And then I take a sample, I measure sugar content in every apple from my sample, and then I compute the average. And then you can see that the average is actually below 10, although I assume that for population, the average should be 10 or above. And the question is, how likely is it possible to get a sample with this average if in fact population has this average? Okay, that's exactly what hypothesis testing does. It assesses how extreme your current sample is for given assumption about the population. So how likely, if you repeat the experiment again, you can get a sample which looks as your current sample or maybe even worse for this assumption, assuming that indeed it came from this population. So that's the overall idea. Let's talk about details. Well, first of all, let me remind you that sample average and population average can be linked by, well, strictly speaking, it's normal distribution, but we realized that in the previous learning sequence, we cannot use normal distribution without knowing the population standard deviation. So therefore, we use approximation of normal distribution, which is called t-distribution. If you use t-distribution, then the average of your sample and the average of your population are linked. And we know that average of your sample is a random number. It varies randomly around average of your population, and this is the magnitude of this variation. So we can say that this distribution, t-distribution, it's a kind of portal, it's a kind of a door between two worlds. One world, it's a population world where we have fixed parameters, and one world, it's a sample world where your statistics of your sample are random every time you take a new sample. Okay, so that gives you a possibility to travel between these two worlds. And these are statistics of our sample that we actually calculated also in the previous learning sequence. So this is the sample size. I'm talking about these 5 apples. This is the average sugar content, standard deviation, and this is the standard error, where I take the standard deviation and divide to square root of the sample size. Okay. Now look, because it's a door, it's a portal, it can work in both ways. So far, we learned this way, how to get from sample to population using this distribution, right? In this case, we have 3 steps, right? First of all, we define a probability. And for example, for confidence intervals, this probability is related to confidence level, right? Then based on this probability, we compute t-value using theoretical distribution, using ICDF function for theoretical distribution. And then we use these t-values, computed t-values, and also the statistics of your sample to compute the population parameter. So we go from sample to population via theoretical distribution. So this is an example. If you want to compute confidence interval, so we have 95% of most common values, so we can define probabilities. The first probability, it's a probability for the left part, for the left boundary of this interval. It will be 2.5, 0.025. You remember why? Because if we have 95 in between, this area will be 0.95. It means that area for this, for the left boundary here, the area on the left of the left boundary will be 0.025, right? So we define a probability, right? Probability. Then we compute t-score, t value, based on this probability. How? Well, we just use a t-distribution, right? So we say quantile function for t-distribution. The probability is 0.025, and then degrees of freedom is 4, because we have our sample size is 5 in this case. If you run this in R, you will get exactly this value, right? And then based on this t-score and based on the all statistics, we can compute average, right? So in this case, look, t-score is known, S is known, N is known, M is known. So the only unknown in this equation, it's mu, and then we can compute this unknown mu by simply putting all together. And this is our estimate for the left boundary of our confidence interval, right? Likewise, we can compute the right boundary, right? Again, we define a probability, so that's the first step. In this case, we define a probability for the right boundary, and you remember that's area on the left, right? So this is 0.975. Then again, we use QT, the ICDF function for t-distribution, but instead of 0.025, we use this probability 0.975. We compute the t-score, and then we use t-score to compute the mu, the average of population, possible, of course, average of population, our estimate for the right boundary of our interval. That's exactly what we've been doing in the last learning sequence. Now let's learn how to do it other way around, how to go the other direction, the opposite direction. And that's exactly what hypothesis testing is. So therefore, you can see my slide title, two sides of the same coin, because strictly speaking, we use the same distribution, we use the same like a door, the same portal, but just go in opposite direction. So in the opposite direction, we should have an assumption about population parameters. So we should pretend that we know mu. We will discuss how we get this knowledge in a minute. And then based on this assumption, we compute a probability to get a sample as extreme as you have for this particular assumption, or more extreme, assuming that your assumption is correct. Let me show you an example again. Now you can see that we went this way, now we go this way, right? So first of all, we defined mu, then we compute t-value, but this time we compute it not based on the probability, we compute it based on mu. So the t-value will be empirical t-value, not theoretical t-value. And then we compute a probability for this empirical t-value. So let me show you an example again. So let's first of all define mu. So I will say that we expect that average sugar content in all apples in our garden, for example, in our population, is 10 or above, 10 grams per 100 gram of apple mass, so 10 weight% or above. So this is my assumption about mu. Now I compute the t-value first. So the t-value, again, I use this expression, right? You can see that. Let me write it down again here. If m is equal to mu plus Ts over square root of n. If we subtract mu from both sides, we will get m minus mu on the left side equal to Ts over square root of n on the right side. Now, if we divide both sides to s over square root of n, we will get the following: m minus mu divided to s over square root of n equal to t. So this is how to compute t if you know m, if you know mu. In this case, you can see that we have mu larger or equal to 10, and we take the boundary value, in this case 10. We know s, we know square root of n. So we can compute our t-score based on our assumption, based on the value that we pretend to know about the population and the sample statistics. So in this case, it's minus 2.5. What's the meaning of this minus 2.5? We will discuss in a minute. But so far, let's just finish. Let's take the final step. So if this is minus 2.5, what's the probability then? So the probability to get a value minus 2.5 or even smaller, because in this case, your sample will be even more extreme for your population, because your sample in this case will have even smaller average, right? So in this case, we simply compute it as a left tail, right? So we know that this is minus 2.5. Probability to get minus 2.5 or smaller, it's this area. And that's exactly 0.033. So this, the outcome of hypothesis testing. This is the probability to get a sample as extreme as you have. It means it has as little sugar content as our sample or even less. Okay. So this is just an overview of the whole actually learning sequence. Now let's take and consider all these calculations step by step and understand every step. So first of all, let's talk about calculation of t and the meaning of this t value, right? So remember, this is how we compute t. So we take, we use the same expression, the t distribution with a link between m and mu, and then we just pretend that we know mu. So in this case, we set mu to equal to 10 grams. Now you can say why we set mu equal to 10, although in our assumption mu is equal or larger than 10. The idea is following. If you look at this assumption that we have here, you can split it into two parts. First of all, it's the number. So in this case, mu is equal to 10. And then the direction, or greater, right? So we say, we expect that average of population is equal to 10 or greater. This or greater defines a direction, while the number defines the expected value. And when we calculate t-score, we always use the expected value. And when we calculate probability, then we use a direction. Okay. This assumption, together the expected value and the direction, is called a null hypothesis, and it's usually denoted by H0. So that's our null hypothesis. That's our default hypothesis, default assumption about our population. Okay. Now let's get back and discuss how we compute the t-score, right? So we have our null assumption, mu is equal or larger than 10 grams, and therefore the value for this null assumption is 10 grams. Now what we do, we first of all measure how far the sample average is from the assumed population average. So how extreme our sample is, right? In ideal case, sample average and population average should be the same, but of course you will never have the ideal case. Your sample will always be different from the population average. Your sample average will always be different from the population average, and we just measure the magnitude of this difference. So in this case, it will be minus 0.5, right? Then we divide it to standard error. But remember, what is standard error? Standard error, it's a measure of distance in t-distribution, right? So we simply, this 0.2 means it's 0.2 grams in one standard error. It's like we computed z-score for normal distribution. It's very similar procedure. So the final value, this one, it tells us the difference between expected average, the population average, and the sample average in standard errors. It means that the sample average is by 2.5 standard errors smaller than population average. So that's the meaning of this t-score. What you see here, it's a t-distribution. This is standardized t-distribution, so it means it's a distribution of t-values. And this is, I use t-distribution to show you distribution of m values, of average values of your sample, right? So here you have the expected mean, it's equal, expected mu, it's equal to 10. So if m is equal to 10, then you will be here, your sample will be here. But if m is equal to mu, if m is equal to 10 and mu equal to 10, then the t-score will be 0, right? Then m minus mu will be 0. So this is our expected value, t-score equal to 0. Our t is here, right? Why our t is here? Because it's 2.5 standard errors below the expected value, right? So this is the 2.5 standard errors below, but it corresponds to 0.5 grams below the average of assumed population average, right? This is 10 grams, this is what we assume, this is our sample average 9.5, right? So here the distance is in grams, because we're talking about average values. Here the distance is in standard error. So that's the main idea of the t-score. T-score, it's a standardized distance in standard error. Now, let's talk about direction, right? You remember that our hypothesis is mu is equal or larger than 10. So it means that this is your sample, 9.5. If you have a sample which will have average value larger than 9.5, these samples will be better for our population. So they will suit better our population because they are closer to the assumption, right? So it means that all this direction, it's a good direction. These samples are less extreme than the sample that we have. Likely here, the t-score, if t-score gets towards positive values, so from minus 2.5 towards positive values, that's the good direction. All these samples, they will be either as extreme as our sample or less extreme to this hypothesis, right? So this area is area of good samples. What will be the area of, so to speak, bad samples? Samples that are even more extreme than sample that we have. Apparently, it will be the opposite area, this one, right? So in this case, we have like 9 or maybe even 8 or 7, and we assume it should be 10 or larger, but here we have samples with very, very small average sugar content. So all these samples are more extreme to our hypothesis, right? And then likewise in t-score, right? So all the samples will have t-score going towards the negative values. So this is the direction of more extreme samples. And now what we need to do, we need to compute a probability to get a sample which is either as extreme as we have or more extreme. And that's exactly this area. That's the probability, if null hypothesis is true, that's the probability to get a sample which is as extreme as our sample or more extreme. Okay. And now we can compute this probability. How we can compute it? We can use a CDF function for t-distribution in R. This is our t-score. This is our degrees of freedom. And that gives you exactly the probability. You can see 0.033 or 3.3%. If you repeat this experiment many times, taking 5 apples, measuring sugar content, and if null hypothesis is true, then approximately 3.3% of our samples will have average 9.5 or smaller, meaning will have t-score minus 2.5 or smaller. So that's what hypothesis testing is in this case, hypothesis testing for the population average. Okay. So this is the probability. You can interpret this probability in several ways. The first way, it's a chance to get a sample of size 5 whose average will be 9.5 or below, although it came from population mu equal or larger than 10, right? So it means that if null hypothesis is true, that's the probability to get a sample with 9.5 grams in average sugar content in average or smaller. Or you can interpret this as a chance to get a sample with t-score equal or smaller than minus 2.5. Or it's a chance to get a sample as extreme as our or more extreme if null hypothesis is true. All these interpretations are equal, it's just different wordings, right? So this interpretation is more formal, while this interpretation is more like a human worded, so to speak, without any math here. Okay. We will talk more and more about the p-value, so if you still feel like you don't understand it in full, don't worry. At the end of this learning sequence, you will definitely understand the meaning of the p-value. Now you know both ways to make an inference. So first of all, we make an inference by computing confidence interval for the population average. It shows you where, in which boundaries, in which interval the real population average is. And the second way to make an inference, it's to make a test. It's to make an assumption about the parameter of your population and then compute a probability to get a sample as extreme as you have or more extreme, considering that your assumption is correct. So that's exactly what hypothesis testing is. And then, for example, another interpretation can be if you take 1,000 samples of size 5, so if you repeat this 1,000 times, taking 5 apples, measuring sugar, computing average, and if indeed for the population this is true, then 3.3% of your samples, which is 33 samples out of 1,000, will have the sugar content 9.5 or smaller, right? So that's the interpretation, another interpretation of this p-value. Now, in order to make even better understanding of the meaning of the p-values, I recommend you to take this Grasta app, and in order to help you with that, the next video will be about this application, which is exactly explanation of what p-value is, just in a slightly different way. Okay, so please watch the video about this Grasta app, then go to Grasta and play with this app, and then come back for the next part.